Yeah, so the next group of questions, 21, 22, 23, 24, 25, and 27. All right, so we just talked about Q and K and comparing the two, right? And so again, K is equilibrium, right? That's where a reaction wants to be at equilibrium. Q tells us where the reaction is relative to that. So we have to know both values. A Q can tell us where will a reaction move. So if a product concentrations are greater than reactant concentrations at equilibrium, no, K is going to tell us that because K is all about equilibrium. If reactant concentrations are greater, no, again, that's going to come from K because it's about equilibrium. Temperature and pressure combination to attain equilibrium. Again, no, we actually don't know that, anything given here. But D, right, Q tells us the direction, right? What direction? We just saw that from the previous question, right? When Q is greater than K, the reaction is going to move to the left to get to equilibrium. And so that's what Q tells us. The direction a reaction will move to reach equilibrium. For question 22, right, they give us this reaction and then they say, right, here's the equilibrium constant for that reaction. And then they ask, what is the equilibrium constant for the reverse reaction? And so if we know the equilibrium constant for a forward reaction, right, the equilibrium constant for the reverse reaction is simply the inverse, because for the forward reaction, right, N2O4 going to 2NO2, that equilibrium is 6.1 times 10 to the minus 3. We flip that reaction, 2NO2 goes to N2O4. That's going to flip the numerator and denominator because K is always products over reactants. And so it's going to be the inverse of what we have. So 1 over 6.1 times 10 to the minus 3, which should also make sense because for this first reaction, K is small, which means the reaction is not favorable, which means the reverse reaction needs to be favorable, right? One of these reactions needs to have a K larger than 1. So 6.1 times 10 to the minus 3, 1 divided by that. Oops. And yeah, I get like 164, right? My equilibrium constant equals 164, which, yes, is larger than 1. And so that means this reaction, let's see, this reaction as written is not favorable, but the reverse reaction should be. The reverse should always be 1 over my initial equilibrium constant. All right, question 23. So yeah, it's a KP, right? The equilibrium reaction mixture of this reaction has the following partial pressures. What is KP? So yeah, this should be a pretty straightforward question where you just have to come up with the expression and then plug in the values. So KP for this reaction would be partial pressure of NO2 times partial pressure of nitrous oxide all over partial pressure of nitrogen monoxide cubed because of that coefficient 3. We'll plug in the values we know. So nitrogen dioxide is 0.642, nitrous 0.225, and then nitrogen monoxide is 1.25. Cube that, and so 0.642 times 0.225, 0.144 divided by 1.25 cubed is 1.95. And so I get 0.07 I guess 40 if we round it up. Yeah, so I would say choice B. So yeah, for something like this, always just make sure you've got the equilibrium expression set up correctly. Remember your coefficients, right? So Tina's question, why did you put the 3NO at the bottom of the fraction, right? Because it's always products over reactants, right? It's always products over reactants. And so the nitrogen monoxide, kind of hard to see because I wrote over it, right? That is a reactant. And then these two are my products in that. What am I missing? It is on the left side of this reaction. All right, yeah, I was just making sure I wasn't missing something there, right? We start with the nitrogen monoxide, we end with nitrogen dioxide, nitrous oxide. All right, question 24, equilibrium, right, has the following equilibrium constant at 300 K, given the partial pressure. Okay, yeah, what is the partial pressure of N2O? So this one is just a similar take, right, on the previous one. So we'll come up with our KP. For this one, right, partial pressure of NO2 squared, partial pressure of chlorine over partial pressure of NOCl. And two of those, so that's squared. So plug in what we have, right? 1.18 times 10 to the minus 3 equals, let's see, what do I know here? So we're looking for the nitrogen dioxide, so that we would just call that X. I don't know that concentration. Chlorine concentration, 0.121, and then NOCl is 0.322 squared. Let's see, multiply, so 0.322, we'll square that, and then multiply that across. So multiply that by 1.18 times 10 to the minus 3. And I get 1.22 times 10 to the minus 4 equals X squared. Divide both sides by 0.121. We get X squared equals, so divide that by 0.121. X squared equals 1.01 times 10 to the minus 3, square root of both sides, and that'll be X. That'll be our concentration, right, of nitrogen dioxide. So second square root and I get a concentration of about 0.0318. So yeah, choice C here, 3.18 times 10 to the minus 2 for our concentration. I think maybe some of you would probably be inclined to call this 2x, right? We don't need to call this 2x, even though there's a coefficient of 2 there, we can just call this x because it's the only thing we're looking for. So it's the only concentration we're looking for. So we can just get away with calling it x. All right, last two questions, 25 and 27. All right, 25, our ice table, and then 27, oh, Le Chatelier's principle. Yeah, we set up the following reaction. Here's our initial concentration of nitrogen and hydrogen, 0 ammonia. We let the reaction reach equilibrium. At equilibrium, we go in and check, and we find that at equilibrium, I've got 0.420 ammonia. What is the equilibrium constant for this reaction? So we can set it up in terms of X first. And so the reaction is, I guess the reaction wasn't written. All right, yields 2 ammonia. So basically, I'm going to lose X amount of nitrogen, and then I'm going to lose 3 times as much hydrogen, and then I'm going to make 2 times the ammonia. All right, we subtract here because these are both reactants. These are both consumed in the reaction. We add here because this is a product. This is made in the reaction. Its concentration is going up. We're going to use the last one to find my concentration, right? I start with 0, I end with 0.42, so we know 2x equals 0.42, divide both sides by 2, and we know x equals 0.21. So yeah, on the exam, I thought I meant to type it in here. Maybe it just didn't transfer over when I was typing out these questions. But yeah, I will give you the balanced chemical equation on the exam. All right, so plus 0.42. So here we're going to subtract 0.210. And then here 3 times that. So we're going to subtract 0.630. Go through, do that subtraction. So 0.732 minus 0.21. And I get 0.522. 1.23 minus 0.630, and I get 0.6. Now we've got our equilibrium concentrations, right? We can go through and find our constant for this reaction. So Kc equals my concentration of ammonia squared over my concentration of nitrogen times my concentration of hydrogen. All right, Kc, my concentration of ammonia, 0.42 squared over my concentration of nitrogen, 0.522 times my concentration of hydrogen, 0.6 cubed. All right, Kc equals, so 0.4 squared, 0.1764 over 0.6 cubed times 0.522. I get 0.1127. Divide those two, and then there's our equilibrium constant. So divide that, and I get something like 1.56. All right, last question, question 27. All right, Le Chatelier's principle, consider the exothermic reaction at equilibrium. Match the changes with the corresponding effect. All right, increasing the volume of the container. So increasing the volume of the container, that favors the side with more moles in the gas phase, because more moles want to occupy and can occupy a larger volume. So if we increase the volume of the container, all right, the equilibrium, we should move the equilibrium to favor the side with more moles. I've got 7 moles here, got 2 moles here. So that should shift the equilibrium to the right. adding a catalyst, right? Adding a catalyst, we get to the same equilibrium just faster. So that has no effect. And then if we remove, and I think I should have put this as a gas, that should be a gas, but if we remove that hydrazine, right, Le Chatelier's principle says equilibrium will shift in a way to replace what was lost. So if we remove some of this from the reaction, equilibrium shifts in a way to replace that. So the equilibrium is going to shift to the left to replace what was lost. So there's a brief rundown of some of the important concepts of Le Chatelier's principle. I'll stop the video there, but we've got like 8 minutes left. If you've got any other questions or anything.